This video is sponsored by Beckhoff. Hi, I'm Miles Budimir with Design World Magazine, and we're here with another installment in our ongoing Motion Control Basics series. And today we're here to talk about motion control networks. Multi-axis motion control typically uses event-based synchronization. This level of synchronization is defined as scheduled, absolute hard delivery of time-critical cyclic data across the network. Delivery variability must be less than 1 microsecond, which is also known as jitter. While a number of networks exist for motion control, it's important to define the time delivery needs for the given application. Synchronized multi-axis motion will have different timing needs than a simple actuator on a conveyor system, for instance. A requirement for jitter-free motion can narrow network choices. So here's a brief overview of a few common networks used in motion control applications. The first one is EtherCAT, or Ethernet for Control Automation Technology, developed by Beckhoff. It's fast and deterministic and processes data using dedicated hardware and software. It uses a full duplex master-slave configuration and accommodates any topology. It can process 1,000 I/O points in 30 microseconds and communicate with 100 servo axes in 100 microseconds. Axes receive set values and control data and report actual position and status. The distributed clock technique synchronizes the axes with less than 1 microsecond of jitter. This protocol can deliver fast throughput because messages are processed in hardware before they're forwarded to the next slave. Slaves read data relevant to them as the data frame passes, and they insert new data into that same data stream on the fly. This procedure doesn't depend on the runtime of the protocol stack, so processing delays are typically just a few nanoseconds. EtherCAT can be configured to interoperate with other TCP/IP networks, including Ethernet versions. It can work with UDP in a protocol stack, although it won't be deterministic. Also, switches and routers between the master and the slaves will negate determinism. Lastly, this protocol is compatible with Circos. The next network is Ethernet IP. Standard Ethernet can't guarantee jitter of less than 1 microsecond because of the data layer's use of the carrier sense multiple access collision detection, or CSMACD, techniques to control packet transmission. To overcome this issue, the ODVA developed Ethernet IP, and it did so without changing any of the 4 lower layers of Ethernet. Ethernet IP is an industrial application layer protocol operating over the Ethernet medium and used for communication between industrial control systems and their components, such as programmable automation controllers, programmable logic controllers, or I/O systems. The IP in Ethernet IP stands for Industrial Protocol, referring to Rockwell Automation's adoption of Common Industrial Protocol, or CIP, standards as Ethernet IP was developed. Ethernet IP with CIP motion as the application layer removes the requirement for strict determinism from the network infrastructure and entrusts the end devices with the timing information necessary to handle the real-time control needs of the application. So this network can deliver the high-performance deterministic control required for closed-loop drive operation using standard unmodified Ethernet. CIP is also used by DeviceNet and ControlNet, so these networks are interoperable. CIP motion accomplishes real-time data transmission through the application profiles that define the technology. Those profiles allow position, speed, and torque loops to be set within a drive. This protocol makes use of CIP sync technology, the IEEE 1588 compliant precision clock synchronization, which is also mapped into the CIP object model to coordinate precise synchronized motion control. Lastly is Circos, a digital bus that interconnects motion controls, drives, I/O, sensors, and actuators from numerically controlled machines and systems. It's designed for high-speed serial communication of standard closed-loop real-time data over a noise-immune fiber optic ring, Circos 1 and 2, or industrial Ethernet cable, Circos 3. In a Circos interface system, all servo loops are normally closed in the drive to reduce the computational load on the motion controller and synchronize more motion axes than it otherwise could. In addition, closing all the servo loops in the drive reduces the effect of the transport delay between the motion control and drive. Circos 3 is the open IEC standard 3rd generation version that transmits data over industrial Ethernet cabling and combines the best of both Ethernet and previous Circos designs for deterministic, bidirectional, real-time motion and I/O control. It delivers rich I/O communication capabilities while enabling all conventional protocols to be transmitted over the same Ethernet network efficiently in parallel with Circos real-time communication. Circos 3 achieves cycle times as low as 31.25 microseconds and supports up to 511 slave devices in one network, with multiple networks possible in a system.